Let us read the question exactly as an examiner would. The graph shows the current voltage characteristic of a Zener diode with 4 labeled portions, a B, B, C, C, D and D, E. We must choose the part most relevant when the diode is used as a voltage regulator. Do not decide from the steepness alone. First identify the bias condition, then ask what property a regulator needs. The correct region must allow current to change while the voltage across the diode remains almost constant. Start by mapping the graph. Positive voltage and positive current form the forward bias quadrant. The curve rises slowly near B, then very rapidly towards A. On the left is reverse bias. From C towards D, only a very small reverse current flows. Beyond the knee at D, the current increases sharply downward towards E. This last portion is the reverse breakdown region. For a Zener diode, that breakdown is intentional and safe when the current is limited by a series resistor. Now translate the words voltage regulator into a graph condition. A regulator should hold the output voltage nearly fixed even when the supply voltage or load current changes. On an IV graph, that means a large change in current should produce only a very small change in voltage. In other words, the operating region must have very small dynamic resistance, defined as delta V divided by delta I. A nearly vertical characteristic is therefore useful, provided it occurs at the required reverse voltage. Check the forward bias side first. Segment AB belongs to strong forward conduction, and BC is the low current region around the origin and forward knee. An ordinary forward bias diode can clamp near its forward drop, but that is not the defining voltage regulator operation of a Zener diode. The question specifically tests the special Zener property, controlled reverse breakdown at a rated Zener voltage. So the forward portions AB and BC are eliminated. Next, examine segment CD in reverse bias before breakdown. Here the reverse current is only a tiny leakage current. The diode is almost open circuit, so it cannot absorb the current variations needed to stabilize a load voltage. Also, the reverse voltage is still changing as we move along this region. There is no strong clamping action yet. Segment CD only leads us to the breakdown knee at D. It is not the practical regulating region. The key portion is DE. After the Zener voltage is reached, reverse current can change over a wide range while the voltage across the diode changes only slightly. Graphically, DE is almost vertical. Mathematically, its small slope in the voltage versus current sense gives a low dynamic resistance. Therefore, the diode can maintain Vout approximately equal to Vz. The current must still remain between the minimum current needed for breakdown and the maximum safe current set by the power rating. See how this works in a regulator circuit. The Zener diode is connected in reverse bias across the load, and a series resistor limits current from the supply. If the supply rises, extra current is diverted through the Zener, but the load voltage remains close to Vz. If the load draws more current, the Zener current decreases. As long as the operating point stays on segment DE, these current changes cause only a small voltage change. That is the regulating action shown by the graph. Now match the conclusion with the options. AB and BC are forward bias portions. CD is reverse bias before breakdown. DE is the reverse breakdown region where the voltage is nearly constant over a substantial current range. Therefore, the part most relevant for voltage regulation is DE. In the source, that is option number 4, Answer ID 336596. Final checkpoint. Zener regulator means reverse bias breakdown region, low dynamic resistance and nearly constant Zener voltage.